Now, one of the things that you're going to need to be able to do is you're going to need to be able to graph linear inequalities. So if you don't remember how to do that, you want to Google graphing linear inequalities, and I am sure that there is a great video for you to watch. I know that I've made some videos, not that they're great, but I know that I've got some videos too that I can provide you as well. But let's get to it. So we're going to maximize, this is our objective function. So this is our objective function. We want to maximize the z value. The reason I know it's maximize is because it says maximize. And it's subject to some restrictions that we have. So some restrictions that we have are on or come from these inequalities. I'm going to put this into slope-intercept form. So I'm going to have y is less than or equal to negative 4/5 x plus 7. And this second inequality, y is less than or equal to negative 1/5 x plus 4. So I'm going to graph the first one. Y is less than or equal to negative 4/5 x plus 7. We're going to go up to 7 on the y-axis, and then we're going to go down 4, and then right 1, 2, 3, 4, 5. Down 4, right 1, 2, 3, 4, 5. And then I'm going to take out my straight edge, and I'm going to draw a straight line that goes through those 3 points. Y is less than, therefore we're going to be shading below the line. My second inequality, y is less than or equal to negative 1/5 x plus 4, has a y-intercept of 4. And I'm going to go down 1, right 1, 2, 3, 4, 5. Down 1, right 1, 2, 3, 4, 5. What's nice about this one is that these two lines intersected in a very convenient spot. They intersected at this point right here in red. I'm going to go back to the gray, and I'm going to look at y is less than, so that is also shading below the line. Then we have y is greater than 0. Y is greater than 0 is a horizontal line on the x-axis. Greater than 0 shades above, and then we have x is greater than or equal to 0, and that is going to shade to the right. So we have a lattice point right here, one right here. We have one right here, which is not a lattice point, and then we have one right here at 0, 0. And I'm going to color that in. I'm going to shade it in with highlighter. So there's our feasible region, and the vertices are, I'm going to take this blue one and show you. That blue one is this very first line that we graphed. It's this one right here. What is the x-intercept? What is the x-intercept of that line? Because that's our vertex of our feasible region. The x-intercept is the value of x when y is 0. So 4x plus 0 equals 35. X is going to equal 35/4. So this ordered pair is 35/4, comma 0. This ordered pair is right 5 up 3. This ordered pair is 0, 1, 2, 3, 4. And then our last vertex is 0, 0. So there's all the vertices of our feasible region. So I'm going to write them 0, 0, 0, 4, 5, 3, and 35/4, comma 0. Now, our objective function is z equals 8x plus 2y. I'm going to put 0, 0 in, and I get z equals 0. I'm going to put 0, comma 4 in, and I get 0 equals 8. 5, comma 3, and I get 46. Doing pretty well right now. And then 35/4 times 8 is 70 plus 0 is 70. We wanted to maximize, therefore 35/4, comma 0 maximizes z to be 70. So one more step before actually maximizing or minimizing is the step before, which is graphing those inequalities. Now, when you have, I'll give you a quick refresher. If you have y is greater than or y is greater than or equal to, we shade above. Greater than or equal to is a solid line. Greater than is a dashed line. That's a dashed line. If we have y is less than, or y is less than or equal to, we shade below. We shade below that line. If we have x is greater than, or x is greater than or equal to, we shade to the right of that vertical line. And if we have x is less than, or x is less than or equal to, we shade to the left of that vertical line. So that's because these are vertical lines. So let's try another one. And I think maybe with this one we might be good to go. So let's try this. We've got y is greater than or equal to negative 3/4 x plus 3. If you need to take the time to make sure that you can do that on your own, go ahead and do that below. You're going to flip the inequality symbol if you divide by a negative. Remember that rule, that you have to flip the inequality sign if you ever divide by a negative. We're just subtracting 3x and then dividing by positive 4, so no dividing by a negative causing us to do that. Here we've got y is less than or equal to negative 1/2 x plus 5, and then we have x is greater than or equal to 0, and x is less than or equal to 4. So we're going to have two vertical lines. So I'm going to do these in colors, this way you can see. You may need that little reminder may help you, how to graph. If I go a little bit slow here, we're going to have a y-intercept of 3. And then we're going to go down 1, 2, 3 and over, or right 4. I don't typically like to say over. This is a solid line, and y is greater than, so that's going to get shaded above. So I just draw arrows shading above. Then the next one, let's do the next one in green. we have a y-intercept of 5, and then down 1, right 2, down 1, right 2, down 1, right 2, down 1, right 2, up 1, left 2. So it is going to eventually intersect. Let's fix that. And I should have gone just one more, because that does go through the x-axis right at x equals 10. They are eventually, they don't have the same slope, so they are eventually going to intersect. Y is less than, that's going to be shading below the line. So far, if these were our only two lines, we would have this feasible region right here. But we have two vertical lines that we need to worry about. So we're going to do this next one, x is greater than or equal to 0. We'll do this one in red. That's a vertical line. Actually, I can keep that a little on the thicker side. There we go. X is greater than or equal to 0, so that's going to shade to the right. So we're getting, we've got three sides now. We've got the green, the red, and the blue side. Now x is less than or equal to 4. X is less than or equal to 4. So here's that vertical line, and less than shades to the left for vertical lines. So we're talking about, let's make this purple, vertices right there, and our feasible region is in blue this time. Now, if those points land on lattice points, then we're in really good shape, and I believe we are in really good shape right here. So we've got 0, 3. We've got 0, 5 right above it. We've got 4, 3. And we've got 4, 0. Those are our vertices of our feasible region. And now it's time to see which one minimizes z equals x minus 2y. I would press pause here, because at this point you can try these completely on your own, because we've done 4 examples of just putting maximum minimums in. What we're now practicing on really is graphing these constraints. So coming up with our values for z, that should be fairly simple. We've got z equals -6, z equals -10, z equals -2, and z equals 4. We want to minimize, therefore 0, 5 minimizes, and our minimum is equal to -10. Fantastic. Fantastic. Okay, we're going to do one last problem for you to try. So we'll make sure you've got it by doing this one last problem. And I'm going to come back. Well, you're going to come back and you're going to see me go speedy through this. Okay, this line right here is y is less than or equal to x minus 1. It's a solid line. And we shade below. We're going to shade below like that, because y is less than. We had to flip the sign because we divided by that -1 in front of y. The next graph is going to have, watch this, it's going to be y is greater than or equal to -3/2 x plus 9. So y-intercept of 9, down 3, 1, 2, 3, right 2, down 1, 2, 3, right 2. Oh, I like it when they share a lattice point. This is y is greater than, so this is shading above. So far we're looking at this region on the right. X is greater than 0, still to the right. Y is greater than 0, that's above. So you can see that we're going to have this feasible region that is unbounded. Yikes. Unbounded. I need to be careful I don't go below the x-axis there. We're going to have a vertex right there, and there's just two vertices, and that's it. Everything else is unbounded. So we've got a vertex at 6, 0 and another one at 4, 3, and we want to minimize. We want to minimize the objective function, z equals 4x plus 7y. I told you I was going to go through this pretty quickly. Z equals 24. In this one we have 16 plus 21, which is 16 plus 24. 16 plus 21. 16 plus 21 is 37. So we've got 24 and 37. 24 and 37. And we want to minimize this. So when we minimize, the minimum would have been 6, 0. Minimum is equal to 24, and 6, 0 minimizes. Now, minimizes. I do it every time. I just keep, I speak, and then I just leave a whole bunch of letters out of the word. Now, if we were asked, if asked to maximize, there is no maximum. And that's because it's unbounded. No maximum because it's, so sorry, it is unbounded. This is unbounded. It just keeps going to the right. Therefore, it's going to get as large as it possibly can. As large as it possibly can.